Okay, good morning everyone. Am I clearly audible?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, good. So I hope that you can see my screen, and this is where we actually stop. And do you remember what was the question that was asked to you when we stopped last time?
Yes, sir.
Okay, so did you try to solve that question? Yes. Any one of you who actually gave it a try?
Yes, sir. But at last समझ में नहीं आया कि आखिर क्या ही लेंगे concentration blank का.
Okay, so you tried, Pooja, right? You tried,
Yes, sir.
and you couldn't figure out what could be the answer. Okay, anybody else who tried but was unable to get to the answer? Yes, nobody else? Okay, so should I consider that none of you were able to solve the question? Mhm. Okay, just to give you the perspective again that what we were discussing and how did we arrive at the question that was given to you in the last class. I will be now shifting to the slideshow mode, and then we will quickly look into uh, what we understood in the last class and how we arrived at the question. Now, I hope that you people have got this understanding clearly in your mind that what is a blank in a spectrometric analysis. Blank is going to be a mixture of all the reagents except the compound of your interest. Uh, and hence, in case now, the reason why it is prepared is in case anything else apart from your compound of interest is giving you some degree of absorption in the same wavelength range at which you are checking the absorption due to your compound of interest, then the absorption due to other reagent components should be nullified before you record the absorption of your compound of interest. With this intention, we prepare blank. So I gave you this pretty example that if I'm interested in compound A, and if B plus C addition is converting compound A to a colored compound D so that I can quantify indirectly the concentration of compound A, then in while considering such a reaction, we need to consider that the blank should be only B plus C. It means it should contain only the coloring reagent and not the compound of our interest, that is compound A. When we are doing so, then there are a few other things that crop up while we are doing or preparing the blank. And what are those things? The first is that when we are actually preparing the reaction mix, then imagine that there are 5 moles of compound A in your reaction mix. And into that, you add 10 moles of B plus C, which is the coloring reagent. Now, this is going to give you the reaction of 5 moles of A with 5 moles of B plus C to give you 5 moles of D, and the leftover amount of B plus C will be 5 moles. Okay. Now, here the situation was that, say, the D that you are creating with this reaction is giving you an absorption at 540 nanometers. So if we consider that, then at 540 nanometers, the situation would be somewhat like this. Say, for example, imagine that your reaction, the coloring reagent, that is B plus C, 10 moles of B plus C gives you an OD at 540 nanometers, which corresponds to 0.1. And 5 moles of D otherwise gives you an absorption at 540 nanometer that corresponds to 0.5. Now, when you carry out the reaction, along with 5 moles of D, you also get 5 moles of leftover B plus C. So if 10 moles of B plus C is giving you an absorbance of 0.1, 5 moles of B plus C will give you an absorption of 0.05. So in total, the absorption that you will record at 540 nanometer will be a combined absorption of D and B plus C, 5 moles each. So if we take the total absorption value should be around 0.55. But according to the concept of our blank preparation, we are going to take, say, because we added 10 moles of B plus C in order to bring about the reaction of our compound of interest, that is A, we will take 10 moles of B plus C in blank as well, and we will negate the absorption due to this 10 moles of B plus C from the total absorption value that we have got. So if we minus the blank value of absorption from this total value, the resultant absorption, what we get, will be equal to 0.45. Actually, however, we should get an absorption of 0.5. So the question that was put forth in front of you after we have understood this calculation of extent of absorption by your sample and extent of absorption by the components of blank, the question that was given to you was, is your blank really a good blank? Or if it is not, obviously it is not, because it is giving you an absorption of 0.45 instead of 0.5. So there is an error of 0.5 that is getting added here, and you don't want any error while you are measuring the concentration, right? So the question was that what you will do in order to make your blank a good blank, right? So as Pooja said, she at least tried, but I would like to first find out that what did you try, Pooja, in order to figure out that if this is not a good blank, then how you can prepare a good blank?
So whether we will take blank for each sample test tube अलग से मतलब if
Do
we
that.
are taking 10.
Oh, correlate it with what you do during your practicals. Okay. Do you prepare a separate blank for each tube, or do you prepare a
No
single
sir,
blank?
we prepare a single blank,
Right.
but as per the solution for this question I was thinking like
Okay.
that we can take a single blank for each tube
But how
differently,
will you
but
decide then the amount?
yes, but that's the question again appear ki we don't know the unknown concentration of the sample only.
Correct.
So how could we decide the concentration of blank only? So that's why I
Right.
didn't figure out the question's answer.
Okay. Okay. So anybody else has anything to say in this direction?
So can we add 0.05 of B plus C to 0.45 so that our absorption will be accurate 0.5? Because 5 moles are reacting ना, so 5 moles का तो हम ले ही सकते हैं. 10 मोल्स का अगर 0.1 है तो 5 मोल्स का 0.05 है, तो हमारा जो माइनस करके आंसर आएगा उसमें अगर हम 0.05 5 मोल्स का ऐड करेंगे तो हमको अपना एब्जॉर्प्शन एक्यूरेट मिलेगा.
Very correct, Balvinder. But you are actually putting up the same thing what Pooja was trying to address, but in a slightly different manner. Here you can add, no doubt, but the problem is with the unknown, where you don't know the concentration. How do you decide that how much amount you need to add now in order to correct or to get a correct concentration of unknown, right?
Yes, sir.
So for unknown, it's a problem. For standards, it may be resolved by preparing a separate blank for every tube, right? But it's a cumbersome thing. Meaning, how many of you would like to prepare separate blank for all the 5 standards that we normally prepare? I bet no one of you would like it, right? You'll prefer using a single blank, and that is what is actually done. So does that mean that the blank that you prepare and the zero that you adjust by using that blank always has some degree of error in it, and you have to do along with that error? The problem actually crops up more when you are actually decreasing the concentration of the compound of your interest. Okay, so if say instead of 5 moles there are 2 moles of A only in your sample, then the remaining amount will be more, so the extent of absorption will be more, right? Are you getting that point? So is it leading you to some kind of an answer now? At least that was actually a hint for you. Okay, yeah, but okay, go ahead. Yes, Palvinder, were you getting to some answer or?
No, sir. I said I didn't understand the question.
Okay, see, instead of 5 moles here, imagine that there are only 2 moles of A in your sample. Then how much amount of B plus C will be consumed in the reaction? It will be 2 moles, correct? So you will get
Yes, sir.
2 moles of D. So the extent of absorption due to D will be 0.2. However, the leftover amount of B plus C would be 8 moles, right? So the extent of absorption due to B plus C will be 0.08 now. So 0.2 plus 0.08 would be 0.28, out of which you will negate 0.1. So what will be the result that you will be getting?
Point two.
Yes. 0.18, right? So is it somewhere near to 0.2? Compared to 0.45, it is nearer to 0.2, right?
Yes, sir.
Correct. So the situation is like, okay, that was a hint for you. Can you imagine some situation in which you can make the things more appropriate for preparation of blank? Okay, let it be. Maybe I can give you the answer right away. Okay, now this is the answer. Okay, so but to get to the answer, you will have to do some calculations again. Okay, now imagine instead of 10 moles of B plus C in your blank, or the amount that you add in the reaction, instead of 10 moles, imagine that you are adding, okay, imagine that you are adding 100 moles of B plus C. Okay, now again, 100 moles also give you, say, just a consideration. Okay, now imagine that 100 moles give you an absorption of 0.1, out of which 5 moles are used in the reaction. Okay, so how many remaining? B plus C unreacted?
95.
95 moles.
95 moles, right? And if 100 moles give you an absorption of 0.1, what will be the absorption given by 95 moles? Yes, absorption will be 0.095, right?
Yes, sir.
Yes, sir.
Okay, now add 0.095 to 0.5 in order to get to the total absorption that you will get. So it will be around 0.595. Yes,
Yes, sir.
out of which you
Yes,
will
sir.
negate out absorption due to blank, that is 0.1. So what will be the value that you will get? 0.495, right?
Yes, sir.
So is 0.495 close to 0.5?
Yes, sir.
Yes, sir.
Right? It is close to 0.5. So what I am doing here? Are you getting to
Increasing
answer?
the concentration of blank.
Increasing the concentration of coloring reagent in the blank. Okay. So that after the reaction happens, no matter how many molecules of A are there in my sample, after the reaction happens, whatever that is left over is more or less similar to what I added. Okay. Imagine now out of 100, imagine instead of 100, there are 1000 moles of B plus C that I add. And 1000 moles now give me an absorption of 0.1. So after the reaction is done, how many moles will remain? B plus C unreacted?
995.
Yes, 995 moles of B plus C. So the absorption due to 995 will be 0.0995, correct? 0.0995 will get added into the absorption of D, and now the absorbance will be 0.5995, right? Out of which I am negating 0.1, that is the absorption due to 1000 moles of B plus C. So what I will get? The resultant value will be 0.4995. Is it still nearer to 5?
Yes, sir.
Yes, sir.
Yes, sir.
Are you getting to the point?
Yes, sir.
Yes, sir.
Okay.
Yes,
So
sir.
now go back to the tests that you performed during your practical class, say protein estimation. The concentration of protein, if you look at it, it is in terms of micrograms. While when you take alkaline copper, it is in terms of grams. So almost 1,000,000 times more than the concentration of protein. Are you getting the point? You are interested in quantifying protein by, say, Lowry's method. The concentration of protein is in micrograms, while concentration of the coloring reagent, which is alkaline copper and Collins CO-calcium reagent, it is in terms of grams. It's almost 1,000,000 times more than the concentration of proteins. Are you getting my point?
Yes,
Yes,
sir.
sir.
And
Sir.
hence, it is actually said that when you prepare a blank, you add the coloring reagent in a large excess there, so that even after the reaction is done, whatever amount of leftover coloring reagent is present in the reaction mix, that is more or less same to what you have added while to carry out the reaction. So this is called as a large excess addition. And how many of you actually paid attention while doing the protein estimation that you are adding a large excess of coloring reagent? I bet none of you, right?
Yes, sir.
Yes, sir.
Okay, but is it not a point to be understood clearly when you are preparing any of the reaction composition, right? You should actually pay attention to each and every step that you're doing when you're performing the practicals. Okay. 90% of the times what students do is that they just repeat the protocol and they are happy with the results that they get, and then they go back home, right? But imagine what kind of efforts a scientist has to take in order to standardize that protocol for you so that you can use it for your practical understanding. And how many of we do that? Okay, this is
None
nothing.
of us.
Yeah, this is nothing related to what you don't do in the practical. Is actually to bring your attention to very minor points in the practical protocol that you need to pay attention to. So I hope from this point onwards, at least when you perform the practicals, whenever the colleges reopen and you can perform the physical practicals all by yourselves, then you would be able to figure out that why you're using blank and why you're preparing the standards. I hope that I have made the point pretty clear to all of you, right? So,
Yes, sir.
yeah.
Yes, sir.
So was it not interesting to find out that how we prepare actually the blank?
Yes, sir.
Right.
Yes.
Okay. So now, as we know that how the blank is prepared and how we make the situations more, what you can say, precise for concentration analysis by using absorption spectrometry, then the next point comes into play. And that is when we prepare a standard curve, right? So I'm pretty sure that all of you must have prepared a standard curve of Beer-Lambert's law. And that is when you plot concentration of your sample against the optical density or the OD value that you get. And usually, if you look at any experiment, then it is always told to you that you should prepare a standard in a particular range. That means you say, for example, for proteins, you start from somewhere around, say, 0.2 microgram concentration, say 0.2 microgram concentration, and you go to maximum around, say, somewhere around 1 microgram concentration. Okay. And then you prepare a standard curve and you plot the OD values and you get a straight line passing through origin. That is what is expected. Okay. But there is something that is pretty more interesting here. Sometimes you get deviations. Now there could be the deviations of different types. Okay. And the deviations are grouped under two different categories. One is called as a positive deviation. Now you need to understand that what is a positive deviation. Okay, because you might have studied this also in your undergraduate classes. Can anybody tell me what do you understand by the term positive deviation? Yes. Okay, so say for example, according to Beer's law, with increase in concentration, there is increase in absorption. There is proportional increase in absorption, right? What that means is that when I double the concentration, the absorption should also double. Okay. However, there reaches a point where if you increase the concentration, even with a very slight value, now how do you read this graph is pretty important. Okay. Say maximum concentration to which the proportionality situation is followed is this concentration value. If you increase the concentration beyond this value even a little bit further, you don't double it, you just increase it by a very small quantity. You can see that there is an increase in absorption, which is quite large. This is an absorption axis, right? So there is an increase in absorption, it's quite large with very slight increase in concentration. When even by small increase in concentration, there is a large increase in absorption, and it no longer follows the Beer's law now, then that is called as the positive deviation. This much is understood?
Yes, sir.
Okay, so can you now tell me what could be negative deviation? As I gave you the perspective of how you read the graph and how you get to the positive deviation, with slight increase in concentration, there is a large increase in absorption value. That is positive deviation. What could be negative deviation?
Lowering the concentration.
No, if you lower the concentration, then you will land up into the area of proportionality again, right? If I decrease the concentration, there is another possibility, and that is with very slight increase in concentration, there's hardly any change in absorption that you can see. Okay, and if you increase concentration by a very large value, also still there is hardly any change in the absorption characteristics. It's only this much of change. You can see that. I hope that you are understanding how to read the graph. Absorption is seen like this, change here along y-axis, and concentration is seen like this along x-axis. So I'm increasing the concentration by this much value. Ideally, the absorption should have increased proportionally, right? But it doesn't increase with that value, with that change. It changes by a very little value. And that is what is referred to as negative deviation. Is this making sense? So first situation is that when I increase the concentration a little bit beyond this value, then there is a positive deviation. What it indicates is that there is a large increase in the degree of absorption with a very small change in concentration. That is not following Beer's law again. Other way around, there is a possibility that when I increase the concentration by a large value, I expect a large change to happen in the optical density, but it is not happening here. The change is very small. There is very small increment in absorption, although I change the concentration by a magnitude of say 100. Am I making sense?
Yes, sir.
Yes,
Okay.
sir.
So there are two ways in which the deviations can happen. One is a positive deviation when with slight increase in concentration, you get a large increase in absorption. And there is another way of looking at it, that is negative deviation, where with large increase in concentration, there is very small increase in absorbance, which is also not following the Beer's law. So whenever the situations start to happen like this, that the Beer's law doesn't seem to be obeyed, then there could be certain reasons behind it. Okay. The first or the primary reasons could be the instrumentation limitations. Okay. That means your instrument is at fault in the sense that somehow it is not able to read the extent of absorption in a better way. In that situation, we think of that there could be an instrumental error. Okay. However, this is a very less probable situation, and this happens only when there are power fluctuations going on while you are taking the absorbance values. To check whether there is an instrumental error, what you can do is that you can always use blank before checking up the absorption due of any sample. Like this is a what you can say a good practice, that normally what we do is that we put up the blank, we adjust 0, and then we forget about blank, right? We start taking the absorbances of only our samples one after the other. But what if I do it like this, that I take blank in one cuvette, I put it inside the colorimeter or the spectrophotometer, whichever you are using, and I adjust 0. Then I take out the blank, I put my sample inside, check the OD, take out the sample and put the blank again and find out whether it is still 0 or not. Okay, this is a good practice to do. If I do that, then I can check that whether there are instrumentation problems happening. If there is a voltage fluctuation going on in your area, then what will happen is that even the blank will not be 0, will no longer be 0. So you'll have to adjust the blank 0 every time. Have you been to such situations? Okay. Okay.
Yes, sir.
Okay. How many of you actually do this? Meaning you check the blank before checking up the absorption of every sample.
Yes, sir.
You do that. Okay. Very good.
Yes, sir.
That is a very good practice in order to find out that whether there is an instrumentation problem. If, however, there is no such problem, then there could be another situation of high sample concentrations. This most of the time said to happen in case of biological samples. Sometimes, now this is just an example, okay, don't take it very literally. Sometimes it may happen that you are checking the absorption due to amino acids. Okay, say for example, you have taken one particular amino acid and you are checking the absorption of that amino acid with increase in its concentration. After a particular concentration is reached, if it starts to polymerize all by itself, then after a particular concentration, what will happen is that you will get a polymer of that amino acid. The polypeptide you will get. Okay, this is just an example. This doesn't happen. Okay, just an example. But it is possible that if you increase the concentration of that particular amino acid beyond a particular value, then it might start to self-polymerize. And if it polymerizes, the polymer no longer behaves like a free amino acid now. And hence, you will see a deviation from Beer's law. Now, that can be a positive deviation if the polymer absorbs much better at the same wavelength value at which the amino acid was absorbing. If it absorbs better, then it will be a positive deviation. If the polymer doesn't absorb at that particular wavelength value at all, but it absorbs at a completely different wavelength value, then there could be a negative deviation. I hope that this much point is clear.
Yes, sir.
Yes, sir.
Okay. Now there could be temperature effects as well, because with changing temperature, the absorption behavior changes. Because basically increasing temperature leads to vibration of the solvent molecules, and solvent molecules tend to strike faster. Now this is also true about the solute. That means the compound of your interest may also start to vibrate better, and hence because of those vibrational transitions, it might start giving you certain abrupt values with change in temperature. So it's always recommended that you perform absorption studies at a standard, or you can say a specific constant temperature value. Next comes sample instability. Now this is very common that biological samples don't remain stable beyond a particular limit. Like say, for example, we know that RNAs are quite unstable in the sense they start to fragment. And if we are checking, say, for example, RNA concentration after fragmentation, there could be a deviation in absorption characteristics of RNA molecule that is possible. Then there is a possibility of fluorescence as well, or at a very high concentration, there is a possibility that the sample may start precipitating out of your solution. And if it starts to precipitate out, then obviously it will not obey the Beer's law. So these are very commonly observed kind of what you can say situations when you can get deviation from Beer's law. Okay. Now, when you are talking about deviation from Beer's law, then the most important thing that we need to look at is when we get a particular concentration range, we should be very certain that we don't go beyond this value of concentration beyond which we are getting deviation. And this concentration value is referred to as the critical concentration. Okay. Now, if you go beyond this particular concentration value, you might start to get deviation, which could be either negative or positive. As you can see, that the point has deviated away. And hence, we should always be certain that we work below the critical concentration value and we don't go beyond the critical concentration value, so that we work in this window of concentration, which is going to obey the Beer-Lambert's law. Is this much fine with everyone?
Yes, sir.
Yes,
Yes.
sir.
Okay. Now, if you have understood all of this, are you having any questions regarding this? Anybody?
So,
Yes,
as you said, that we should consider the values below the critical concentration point.
correct.
But the in that straight line graph,
Mhm,
that we have got one point on the straight line only,
mhm,
but beyond the critical concentration.
mhm.
So whether it will be not considered while drawing the straight line or not.
No, ideally, see, okay. This is actually a very good question. Okay, what happens sometimes, see, as I have shown over here, you normally, now, although I have shown this as a critical concentration, when you actually plot the standard curve, you don't get all the 5 points on the line, right? How many of you get all the 5 points on the line?
No, so matlab
You don't get it,
maximumly 2 to 3. Yeah, yeah.
right?
Sometimes it's maybe only 2.
Right. So, what I'm trying to convey here with this graph is you should actually consider those points, like we in the last lecture, if you remember, I told you this, that if you're not getting all the 5 points on the line, which points should you consider in order to draw the straight line? Is it necessary that you should get maximum points on the line? Do you consider that as a standard operating practice or a good operating practice? Or you should consider even a single point you can consider, but there should be a situation that should be followed. What do you think? Which is a good way of preparing a standard curve? Like here, I have shown that there are 3 points coming on the line, so I took those three. But there are other 2 points which are lying outside, right? So can I not draw a straight line using these, say, 2 points, or using only this as a single point? Can I not draw a straight line like this? Can I not draw a straight line like this? Can I not take these 2 points and get a straight line passing through origin? Yes. Forget about this point for time being. Don't consider this point. Okay. Say this is not there. Imagine. Can I take, if you're taking only 2 points on the straight line, can I not take these 2 points, say, suppose, and get to the straight line passing through origin instead of taking these 2 points?
Yes, so we
Yes,
can
sir.
draw.
Yes, but I will not recommend you to do that. The reason is simple. When we are actually drawing the straight line, we should always consider such points in a way that other points which are not lying on the line should be on either side of the line in equal proportion. What does that mean is that you are trying to balance the situation. Okay. In the sense, imagine that I take these 2 points, say this 1 point and this the another point I take, and I draw a straight line, say suppose it passes through origin. Say suppose it looks like this. Okay, I have taken these 2 points, say suppose it falls on the line. Okay, don't bother that I'm not getting a very good straight line. But imagine that these two are falling on the line and it's passing through origin, and these two are falling on one side of the line. What does that mean is that when the point falls on one side of the line, this is considered to be a positive deviation, and this is considered to be a negative deviation from Beer's law, right? So if I take the points in such a way that positive deviation points and negative deviation points are lying equally on both sides of the line, then I'm actually reducing the extent of error. So I'm balancing the error. Are you getting the point?
Yes, sir.
Okay. So you should always choose those points so that you get a balanced curve, rather than choosing those points which you'll get a curve which will be a lopsided curve. Okay, imagine that this is the curve that I have drawn, taking these 2 points. Then these 2 points both are positive deviations, right? So that will add to the extent of error that I'm getting. Am I making the point clear?
Yes, sir.
Yes,
Yes,
So
sir.
you cannot arbitrarily choose any points and draw the straight line. You should choose only those points in such a way that when you draw the straight line, on either side of the line, you get equal number of points. Okay, that will make the curve balanced. Now coming to the question that Pooja was trying to ask. Okay, say one point was shown over here beyond the critical concentration. You might not get a deviation, much deviation, sometimes beyond critical concentration as well. But you cannot be certain that beyond critical concentration you are not getting deviation. Okay, sometimes it happens. Now imagine this. You prepare a standard curve using say 0.2 as your minimum concentration standard and concentration of 1 as your maximum concentration. Now imagine beyond this point. Now say, okay, say that you have prepared a standard curve which looks like this. Okay, this should pass through origin. Okay, imagine that this passes through the origin. Now minimum concentration of your standard is 0.2 and maximum concentration of your standards is 0.1. So consider that the critical concentration is 0.1 and beyond this the Beer's law will not be obeyed. Imagine that your unknown gives you an OD which is beyond the OD that corresponds to 1. Say suppose the maximum OD that you have got is 0.5, which corresponds to the concentration of 1. Somewhere the spot appears like here. Okay, so imagine that your unknown sample is giving you an OD of 0.8. This is much beyond the OD of your maximum concentration of standard. How will you find out the concentration of unknown now? Using this standard curve? Is the question clear? Yes. Okay, should I repeat the question for you? Hello, am I audible?
Yes,
yes,
sir.
sir.
Yes,
Okay.
sir.
So should I repeat the question?
No, sir, we
Yes, sir.
understand the question.
You understood the question. Say your unknown gives you an OD of 0.8, which is much beyond the maximum OD that you can get by the maximum concentration of the standard. So the unknown OD is this. And you need to find out what's the concentration of unknown. How do you do it? Yes,
So we can't find.
you cannot find. Okay.
Yes.
But if you can find out, how can you find it out? Have you never been in such situation that the OD of unknown is much beyond the OD of the fifth standard that you have prepared to prepare the standard curve? OD of unknown is
No,
more than the
sir.
OD
No,
of its
sir.
standard.
No,
Okay.
sir.
Okay, you haven't been in such situation. But according to you, theoretically, how you can find it out? Any idea?
सर हम स्ट्रेट लाइन ले लेते जैसे concentration.
Okay,
Straight line.
you just extrapolate this straight line. That's what you're trying to say?
Yes, sir.
Till the point reaches to 0.8 on the y-axis, right?
Yes, sir.
So on the y-axis, you extrapolate the line till you get it intersected with 0.8. And then from this value, you will draw a straight line and you will find out the concentration. This is actually the most incorrect way of doing it. Okay. The reason I will tell you, as I have shown over here, beyond the critical concentration, sometimes it may not obey the Beer's law, right? You don't know that whether it obeys Beer's law or not. And this 0.8 might be either underappreciated OD in the sense that it might be slightly lesser OD than what you should get, or it could be much more than what you could get, because if it is not obeying Beer's law, then you might get either positive deviation or negative deviation beyond say 1. Am I making sense?
Yes,
Yes,
sir.
sir.
Yes,
So
sir.
when you extrapolate, you assume that the Beer's law is obeyed, right? Okay, and this assumption may not be correct. So what you do actually is that you dilute it. You dilute the unknown. Okay, say imagine that I double dilute it, in the sense that whatever be the volume of unknown, I add the same amount of water into it. Okay, so I have double diluted the unknown. I recheck the OD. Okay, now if the OD say drops to 0.35 after double dilution, okay, drops to 0.35. Okay, ideally what I expect when I double dilute is that the OD should be exactly half of this, right?
Yes, sir.
If the sample obeys Beer's law, then the OD should be exactly half of 0.8. But imagine that the OD drops to 0.35. What this tells you is that now 0.35 is in the range. Maximum OD is 0.5 and it is in the range of your standards.
Yes, sir.
So can I not plot 0.35 and find out what is the concentration value? And whatever the concentration I get here now, say I get X concentration, I just multiply it with the dilution factor, which is 2. And I get to the actual concentration. Is it good enough?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, what I am ensuring when I am doing this?
Beer's law should be followed.
Right. But there is one more thing that I am actually figuring out. When I double dilute it and when the OD falls to 0.35 instead of 0.4, what it tells me is that at a concentration beyond 1 and beyond the OD, maximum OD of 0.5, the Beer's law is actually giving me a positive deviation. That means the sample is actually giving me a positive deviation, in the sense that the concentration is such that I should have got an OD of 0.7 instead of 0.8, right? But I'm getting 0.8. That means I'm getting an extra value of OD rather than the actual OD value. Am I making sense?
Yes, sir.
Yes, sir.
Okay, so that also tells me that my sample beyond the critical concentration value is giving me a positive deviation from Beer's law. I hope that I have made this thing pretty clear in your mind. If there are any questions, you can ask me. Okay, I assume that the things are pretty clear now. Okay, if there are no questions, then I have one. Imagine now, when I plot at different wavelengths, when I plot the absorption due to my sample, when it is at a low concentration value. Now this is a low concentration value, below critical concentration. Okay, now this below critical concentration, the pattern of absorption that I see is somewhat like this. On this basis, I can find out at what value of wavelength my compound absorbs maximally. Okay, so this I have labeled as lambda 1. This is the value of wavelength at which my compound at low concentrations absorbs maximally. Okay, now this dotted line that you can see is the same sample, but it behaves slightly differently at high concentration values. This is high concentration of the same sample. Okay, so what I'm actually doing is that I have prepared a low concentration solution of my sample, and I check its absorption characters at different wavelength values, and I plot ODs at different wavelength values. Okay, and get to this kind of a pattern of absorption at different wavelengths, from which I can figure out that at which wavelength the compound absorbs maximally. So at low concentration, it absorbs maximally at a wavelength which I have labeled as lambda 1. Okay, and at high concentration, the same sample behaves differently and has a different pattern of absorption. It, however, continues to absorb at lambda 1, but it also starts to absorb at a different wavelength, and that is lambda 3. This much is fine?
Yes, sir.
Yes, sir.
Okay. Now my question is that at high concentration at lambda 1, it is showing negative deviation, right? That means the extent of OD at high concentration at lambda 1 should have been more, but it is less, right? At low concentration, it is much more at lambda 1, but at high concentration, it drops at lambda 1. So if I check the OD values at low concentration and at high concentration only at lambda 1, I can know that at lambda 1, there is a negative deviation happening. Is this fine?
Yes, sir.
Yes, sir.
Right. Reverse is true for lambda 3. At high concentration, I'm getting higher higher OD, while at low concentration, the OD value is low. So it seems that at lambda 3, with increase in concentration, there is increase in OD. Now, the question is this. High concentration means beyond critical concentration, okay? And low concentration means below critical concentration. Now the question is, if I got such a sample, and if I want to find out the concentration of my sample, unknown solution, which wavelength I should use? Lambda 1 or lambda 3? Is the question clear? Yes. Is the question clear?
Oh, sir. Can you repeat the question?
Okay. At low concentration, at lambda 1, you can see that if I increase the concentration beyond the critical concentration, there is a negative deviation. At lambda 3, you can see that if I increase the concentration beyond the critical concentration, there is a positive deviation. Okay, so at lambda 3, there is a positive deviation. At lambda 1, there is a negative deviation. Now I want to find out the concentration of my sample, which is an unknown solution of the same compound whose graphs are given over here. Okay, of unknown concentration. Say the concentration of my sample is not known to me. At what wavelength I should check in order to find out what's the concentration of my unknown? Is the point clear? The question clear?
Yes, sir.
Yes, sir.
Okay. So it's almost the time now. So what I will do is that I will leave you with this question and you will try to figure out the answer. Okay. And we will discuss the answer tomorrow. Is this fine with you all?
Yes, sir.
Yes, sir.
Sir.
Okay, good. So we'll meet tomorrow again at the same point, same time. Okay. And we'll talk about